A spectrometer is an instrument used to measure properties of light over a specific portion of the electromagnetic spectrum, typically used in spectroscopic analysis to identify materials. The variable measured is most often the light's intensity but could also, for instance, be the polarization state. The independent variable is usually the wavelength of the light or a unit directly proportional to the photon energy, such as wavenumber or electron volts, which is a reciprocal relationship to wavelength. A spectrometer is used in spectroscopy for producing spectral lines and measuring their wavelengths and intensities. Spectrometer is a term that is applied to instruments that operate over a very wide range of wavelengths, from gamma rays and X-rays into the far infrared. If the instrument is designed to measure the spectrum in absolute units rather than relative units, then it is typically called a spectrophotometer. The majority of spectrophotometers are used in spectral regions near the visible spectrum. In general, any particular instrument will operate over a small portion of this total range because of the different techniques used to measure different portions of the spectrum. Below optical frequencies, the spectrum analyzer is a closely related electronic device. Spectroscopes. Spectroscopes are often used in astronomy and some branches of chemistry. Early spectroscopes were simply prisms with graduations marking wavelengths of light. Modern spectroscopes generally use a diffraction grating, a movable slit, and some kind of photodetector, all automated and controlled by a computer. Joseph von Fraunhofer developed the first modern spectroscope by combining a prism, diffraction slit and telescope in a manner that increased the spectral resolution and was reproducible in other laboratories. Fraunhofer also went on to invent the first diffraction spectroscope. Gustav Robert Kirchhoff and Robert Bunsen discovered the application of spectroscopes to chemical analysis and used this approach to discover cesium and rubidium. Kirchhoff and Bunsen's analysis also enabled a chemical explanation of stellar spectra, including Fraunhofer lines. When a material is heated to incandescence, it emits light that is characteristic of the atomic makeup of the material. Particular light frequencies give rise to sharply defined bands on the scale which can be thought of as fingerprints. For example, the element sodium has a very characteristic double yellow band known as the sodium D lines at 588.9950 and 589.5924 nanometers, the color of which will be familiar to anyone who has seen a low-pressure sodium vapor lamp. In the original spectroscope design in the early 19th century, light entered a slit and a collimating lens transformed the light into a thin beam of parallel rays. The light then passed through a prism that refracted the beam into a spectrum because different wavelengths were refracted different amounts due to dispersion. This image was then viewed through a tube with a scale that was transposed upon the spectral image, enabling its direct measurement. With the development of photographic film, the more accurate spectrograph was created. It was based on the same principle as the spectroscope, but it had a camera in place of the viewing tube. In recent years, the electronic circuits built around the photomultiplier tube have replaced the camera, allowing real-time spectrographic analysis with far greater accuracy. Arrays of photosensors are also used in place of film in spectrographic systems. Such spectral analysis, or spectroscopy, has become an important scientific tool for analyzing the composition of unknown material and for studying astronomical phenomena and testing astronomical theories. In modern spectrographs in the UV, visible, and near-IR spectral ranges, the spectrum is generally given in the form of photon number per unit wavelength, wave number, frequency, or energy, with the units indicated by the abscissa. In the mid to far IR, spectra are typically expressed in units of watts per unit wavelength or wave number. In many cases, the spectrum is displayed with the units left implied. Spectrographs. A spectrograph is an instrument that separates an incoming wave into a frequency spectrum. There are several kinds of machines referred to as spectrographs, depending on the precise nature of the waves. The first spectrographs used photographic paper as the detector. The star spectral classification and discovery of the main sequence, Hubble's law and the Hubble sequence were all made with spectrographs that used photographic paper. The plant pigment phytochrome was discovered using a spectrograph. It used living plants as the detector. More recent spectrographs use electronic detectors, such as CCDs, which can be used for both visible and UV light. The exact choice of detector depends on the wavelengths of light to be recorded. A spectrograph is sometimes called polychromator, as an analogy to monochromator. Mass spectrometer. See also, circular dichroism, Schneeturner monochromator, list of light sources, photometry. Main photometry radiometry article, explains technical terms, scanning mobility particle sizer, spectroradiometer, references. Bibliography, J. F. James and R. S. Sternberg, The Design of Optical Spectrometers, James, John, Spectrograph Design Fundamentals ISBN 0-521-86463-1, Browning, John, How to Work with the Spectroscopy, A Manual of Practical Manipulation with Spectroscopes of All Kinds, Palmer, Christopher, Diffraction Grating Handbook, 6th edition, Newport Corporation. 1. External links, Spectrometer at DMOZ.